All right, so we're going to go over how to set up equations when solving for force problems. So these are the topics that we're going to discuss. The idea here is that I'm going to go over, in general, how to work this type of problem. I'm not really concerned with numbers, just making sure that everybody understands the big picture and how the formulas should be designed for these different scenarios, okay? So first we have an object that is on a horizontal surface with no acceleration. So if we have an object that is just simply at rest, so maybe this is your phone sitting on the table. We have a downward force due to gravity, always. And then we have the normal force. And so just a reminder, the normal force is, thanks to Newton's third law, the responding force because of contact between your object and the surface. So for a situation where my object is at rest on the table, these two are balanced. There is no acceleration, which means that I have a net force of 0. If net force is what causes acceleration, no acceleration means a net force of 0. So that means that if I were to add these two forces together, since the force due to gravity is in the negative direction, so in class we've been writing it like this, they would be the same magnitude but one positive, one negative, so they would add up to 0. Okay? If we were looking at the horizontal direction, so let's say that this is an object where it is at rest, but we apply a force to it. Well, if the question tells you that the object does not accelerate, if this is an object that is currently at rest, this would be a situation where I'm pushing or pulling on something, but it doesn't move. Well, why does it not move? Because there's friction between the object and its surface, and that friction is strong enough to fight off your attempted force to move it. So these two forces are also balanced, which means that my net force is 0 because there's no acceleration in the horizontal direction, which means that when I combine these two forces, because my frictional force is in the opposite direction, I'm essentially subtracting them. They are equal magnitudes so that they add up to a value of 0. Now, I also want to address that this would be the exact same setup for an object that is moving, but it has a constant velocity. Once again, constant velocity means no acceleration. Acceleration is caused by a net force. So an object that is moving while receiving a force, but it does not accelerate, that means that the kinetic friction is equal to the applied force. So I may be pushing my box across the floor, so I'm continually applying an applied force to it, but it's also continuing to receive that frictional force. And so my applied force and its frictional force are going to cancel each other out so that that net force is 0. Okay, so this is the idea behind how we set up relationships whenever there is no acceleration. Now, how are you going to work this specifically for your math problems is going to depend on what information you have. If we needed to expand this formula so that I can use the individual mass acceleration, maybe I'm being asked to solve for my coefficient of friction, all of those little details would be expanded so that my mass times acceleration and my mu mg are simply written in the formula, okay? For both of these situations, since I have a net force of 0, you could also choose to say that your applied force is equal to the frictional force, because if I'm going to take this formula and I'm actually going to do my math work with it, I will eventually need to move those forces to opposite sides so that I can plug them in. So you can choose to write it FA equals FF, and then once I go to expand it, this is still how those details are going to be expressed. So I would maybe write my formula like this. It just kind of depends on what information you are working with in the problem, okay? In the vertical direction, it works exactly the same way. My normal force is equal to my gravitational force, so my normal force is the same as the weight, which is a lot of times whenever our formula calls for the normal force, we just kind of replace it with mg, because that's how I calculate the weight of my object, right? All right, now let's talk about what if there is an acceleration. This thing will let me grab my text box. There we go. All right. So if we have an object that is on a horizontal surface and there is an acceleration. So this type of problem, here's my object. So we're going to assume here that we are focusing on an acceleration in the horizontal direction for right now, because that's most often what our questions are about. The fact that I have an acceleration means I have an actual value for my net force, because remember, it's the net force that is responsible for the acceleration that takes place. So if you have a question where your object is accelerating, maybe they tell you in the problem the rate of the acceleration even though it is experiencing friction, or maybe they're asking what the acceleration rate is and that's what you're solving for. The net force is what will determine how much that object accelerates. So in order for me to calculate the acceleration, I first have to know what that net force value is. So how am I going to calculate that? Well, in most of these questions, we're going to have an applied force that is greater than the frictional force. So I'm going to go ahead and just address it this way. My net force is the sum of my forces. And since my frictional force is in the opposite direction, I'll write it like this. I'm going to need to know what this applied force is. So if I don't have it, I could calculate it using MA. And I'm going to need to know what this frictional force is. So if I don't have it, I'm going to calculate it using mu times the normal, which, as I just showed you in the previous problem, would be expanded to mass times gravity. Okay, now how is this going to play out in an actual formula? That's going to depend on the question that you get. How am I going to need to express this? So I'll elaborate on that in just a second. This net force is equivalent to the mass times the acceleration that the object experiences. So you may be looking at this formula right now saying, Miss Espinosa, you haven't showed me a question where you have MA twice. You're right. Typically, the question is going to be written so that you are given the applied force, and perhaps they tell you information about the friction, and they're asking you to solve for your acceleration here. And this is, again, when we're dealing with a horizontal surface, okay? Or perhaps they will want you to calculate the net force, and you'll have enough information so that you can find the applied force, and then you'll just work it this way. So once again, it really just depends on the specifics of the problem, but you need to understand that this formula right here is the relationship for an object that is experiencing an acceleration. There is a net force there, and so we have to make sure that we account for the net force, okay? All right, now let's talk about what if we have an object and it's going to experience a vertical acceleration. And so this is for an object that's on a flat surface. So this would be the question like the lightsaber on your practice work, or I think somewhere you had a question about a bucket that was being lifted. So that's what these questions are about. Let's not use purple, it's too much purple. Okay, so if I have an object, we've got the force due to gravity. But if this object is being lifted, well, first off, it's probably actually not on the ground. So let's get rid of that, okay? If it is being lifted so that it experiences an acceleration, then these forces have to be unbalanced. We're going to assume here that the acceleration is in the upward direction. So that means that my upward force vector needs to be the bigger of the two. This would not be a normal force because it's being lifted due to an applied force, not a return force from the ground because it's being lifted, okay? So here we go back to the concept that the net force is responsible for this acceleration. So I would need to figure out what my net force is by adding these forces together. Now my gravitational force is in the negative direction, so we've been writing it like this. Oh, look at me. I said it's not the normal, and I said the word normal, so I wrote in. This is an applied force. Sorry about that. So then this is how we've been writing it. So this is the relationship that you need to know whenever you are trying to calculate for an accelerating object in the vertical direction. Now, the questions that you're going to get are going to vary. We might tell you the magnitude of the applied force, the magnitude of the gravity or the weight of the object, or we might tell you the magnitude of the net force. You are responsible for understanding the relationship that drives the action. Then you need to interpret the information that you are provided with so that you can expand this formula into the details that you need in order to solve. So without getting into too many specifics, we did talk a little bit today in class about how we would manipulate this formula in order to solve for whatever it is that we are given. So let me just make sure that everybody remembers. The force due to gravity, aka the weight of the object, if we were not provided that value, we could calculate it using mass times gravity. The net force is the product of the mass times the acceleration. And if we knew the net force, but we are looking for maybe the weight, or if for some reason we needed to actually expand this applied force, it would also be MA. Okay, now once again, we're not going to give you an equation where you're going to use all three of these together. You're going to have either the net force or the applied force so that you can plug that in, okay? All right, we talked a little bit today about how you're going to, actually, I'm going to leave that up there for you. We talked today about how if you are calculating for the applied force, so you had some questions about things were being lifted, and we wanted to know, what was that force that was used to actually lift the object? I reminded you that when we do our rearranging here, we are adding the magnitudes of these two forces. So yes, the weight of the object is in the negative direction, but if we were to calculate my weight using mass times gravity, I would normally input a negative 9.8 here, which would give me a negative value for my weight. Okay, but if I take that number and I add it to this other number, I'm actually doing a subtraction because of that negative, right? So you have to make sure that you understand what it is that you are solving for. What is the situation? My applied force needs to be bigger by combining how much the weight is plus the net force. So we are not going to use the negative aspect of this value. We're going to use the absolute value of it. So we're going to use the positive version of whatever that number would be, okay? So that's something that we discussed in class today. Ultimately, it comes down to, do you understand that you're combining these two numbers to figure out how strong the force upward was? So just be careful of that. All right, now let's talk about inclined planes. If we have an object that is on an incline and there is no acceleration, all right? So let's take our surface and let's tilt it. We have our object. We have weight, force due to gravity acting on the object. There is contact between the object and the surface. So we're going to have our normal force. And if you recall from the notes, the normal force is always perpendicular to the surface, all right? So that's where that comes from. Now, if my object is located on an incline, I expect in real life that it's going to slide down because of the weight of the object. Now, the weight is actually pulling straight down. But we've already discussed how this can be broken up into how much of that weight is acting in the same direction as my surface. So parallel to my surface, parallel to my surface. Okay, all of these are along the same plane. So how much of my weight is going to be in the same direction or along the parallel axis to my surface? That's the magnitude of the weight that's going to cause my object to actually slide down the hill. So this would serve as my applied force pulling my object downward, okay? If my object does not accelerate, that means that there is a force that is working to oppose that. And that would be the friction because of the contact between my object and the incline or the ramp. So remember, a net force of 0 means that there is no acceleration. That's what this means, all right? So how am I going to set up a problem for this? The net force is equal to the sum of the forces, but we know that that frictional force is working in the opposite direction. Now, what do you choose to call this first force? You know what? That's up to you. I called it the applied force on this example, so I'm going to go with that. If you want to call it the F of gravity in the horizontal direction, that's fine too, okay? So this is the relationship that you need to know whenever you are solving for a situation where you have an object on an incline but it does not accelerate. Now, how are we going to expand that to give us the details for our problem? My applied force is going to be this horizontal component. So my force can be calculated using mass times gravity because this is the weight of the object specifically. And this is the side opposite the known angle. So if we were to do our little theta here, it would be there. So that makes it the sine function of that diagonal. My force of friction is going to need to be expanded as well. Force of friction in general is going to be mu times the normal. So let's look at my picture. My normal force is on this plane. So normal is because there is contact and it is equal to the weight that's pushing down on the object. So this is the plane that we are working in. So of my weight vector, this is the component or the portion of that vector that's in the same direction as the normal. So when we said way up here at the beginning that the normal force is equal to the gravitational force, that's why we say F normal, which is what the formula for friction says, can be calculated by using the weight of the object. And so for this particular question, the weight of the object is going to be calculated using mg, but it's not the full force component. It's not the full weight of the object. It's the component of the weight that's in the same plane as my normal force. So this side of my gravitational force vector is the cosine of theta. Okay? My net force, if it is not given to me but it needs to be calculated, is just F equals ma. So this will be expanded by doing mass times acceleration. So this is how we would go about expressing these different variables in detail for an object on an incline. And then from here, it's your responsibility to understand how we're going to manipulate the formula moving forward. Now, if it says that we have a net force of 0, this goes away. So we would have our equation looking like this. Well, we can't actually conclude our algebra with something equal to 0. So what I've been showing you in class is that we would probably end up simplifying this to mg sine theta is equal to mu mg cosine theta, because this specifically is for a situation where there is no acceleration. So our forces are balanced. And then you would do your algebra from here. Our last situation is if we have an incline plane where there is an acceleration. So if my object is on an incline, here's my object. This picture starts off the same. We have the weight, force due to gravity. We have the normal, the return force because of Newton's third law, because my object is pushing on the ramp, so the ramp's going to push back. My object is going to be accelerated, typically in the forward direction. So what is going to act as the applied force that causes it to accelerate forward? Well, that applied force is technically the component of the object's weight that is in the same axis as the ramp. So my applied force here would be this gravitational component, which is the sine theta side of my triangle. My frictional force is going to be opposing that motion, and the frictional force, remember, is mu times the normal. The normal force is equal to the weight of the object, and because this is at an angle, it's this component of the weight that's in the same plane as my normal that would be used to be set up equal to the normal force. And this is the cosine of theta side of my weight vector. So now that we've reviewed all of that, our formula is F net is equal to the sum of the forces. And friction is opposing my object's motion. So we would once again expand these different parts of the formula. My net force is mass times acceleration. The force that's serving as my applied force, that's responsible for actually pulling my object down the ramp, is the parallel component to the ramp, which we have been calling the horizontal component, just so we can stick with the horizontal vertical labels that we've been using this semester. So it's the weight of the object, which can be calculated mass times gravity if the weight is not provided. And this is times the sine of theta. My frictional force is going to be expanded by taking the frictional force formula, which is mu times the normal. But if I don't know what that force is, I can calculate it by doing mass times gravity and then multiplying by the cosine of theta because it is the component of the weight. And so this is my formula, and it's exactly the same formula that we started off up here. Why? Because the equation for net force has not changed. It's the sum of your forces. Since we are on an incline plane, it's still going to be the net force is equal to the applied force, which in this case is most often the gravitational force forward, minus the frictional force, which is working in the opposite direction. But for this type of question, my object is experiencing an acceleration. So that means with an acceleration, I'm not canceling anything out. I'm using the full formula, okay? So from here, you are going to be responsible for plugging in the information that you know and doing the algebra to solve for your unknown. Now, for both of these questions, it is possible for these inclined planes that you get questions where you're not provided your mass. So I just want to talk about that, and this is the last point that I want to make to you guys. If we are given a situation where I don't know the mass of my object, I just want to point out to you, in the situation where you have expressed your formula so that mass is present in all of your variables, okay? That's very important. If mass is present in all of your variables, then when you go to solve for whatever it is you're solving for, you are dividing by mass on both sides, assuming you're not solving for the mass. So then, in every situation, your masses cancel, okay? Some of you have not been able to continue a problem that you've set up correctly because you weren't given the mass. And so you felt like without having the mass as a known value, you were not able to continue the problem because you didn't have enough information. If you are ultimately dividing by the mass in your math work, the masses cancel out. So not being provided the mass could potentially not hinder you from finishing the problem. So my recommendation to you is before you decide that you cannot conclude the question without the mass, finish your algebra, go ahead and manipulate your variables and see if your masses cancel, okay? Now, once again, this is only if the formula that you are using does have mass present in every place. So if we were doing a problem where the net force was 0, so my object is not accelerating, this becomes our working equation. So that means that regardless of what variable I'm solving for, unless it's my mass, I'm going to ultimately divide both sides by m. So here, my masses would cancel, but I could continue the problem, okay? So this doesn't work in every situation, but you need to make sure that you are capable of continuing your algebra without the numbers plugged in, because there are going to be situations like these where it's necessary to do that so that you can actually finish the math work. All right? Okay, guys, so this concludes our overview of how to set up the equations with the different types of force problems that you are given. I need you drawing your free body diagrams, and then make sure that you are using those free body diagrams to help you build your equations so that you're accounting for all of the forces acting on the object.